right, what we'll do in this section is we'll solve for several types of equilibrium problems. We'll use the ICE table. In this particular case, solving for a single unknown. Given the type of information that I have in this problem, I don't need an ICE table. What I do need is the equilibrium constant expression, which I get from the balanced chemical equation. And they're giving me the equilibrium concentrations of both of my reactants and simply asking me for the concentration of my one product over here. And they've given me also the equilibrium constant. So I'll write the equilibrium constant expression, which is just going to be the concentration of C at equilibrium divided by the concentration of A at equilibrium. And of course I square them because they each have coefficients of 2. And then we have the concentration of B, which has a coefficient of 1, so it's got 1. Now, what I'm solving for is the concentration of C, because in the problem I'm given that concentration, and I've given K. So really, I only need to solve for the concentration of C. So what I would do here is I would simply multiply by A squared times B. That's going to cancel it over here. I would also do the same thing here. A squared times B. And then to get rid of the squared term, I'm going to be taking the square root. So C is simply going to be the square root of K times A squared times B. Okay, so we'll go ahead and work the whole problem so that we'll make sure that you actually get it. So our K value is 0.100, and our C squared is going to be what we're looking for. So that's going to be C squared. Down here we've got A squared, which is 0.500, and we'll square that term, and this is going to be 0.200 to the first power. We need to make sure that if we're going to throw that in the calculator at some point, we're going to treat this as a product. All right, so I'll multiply both sides by that. That's going to give me 0.100, and that will be times 0.500 squared times 0.200, and that is equal to the concentration of C squared. I simply take the square root of both sides. That gets rid of the squared terms, and that gives me the concentration of C at equilibrium. So let me plug that in, and once I plug that into my calculator, I get 0.0707 molar, and that is my solution. All right, let's take a look at this next problem. We're going to need an ICE table in this. Let's just get some practice filling out the ICE table. I'll do this a couple of different ways here. So we've got this equilibrium reaction, hydrogen gas. This is a gas phase reaction. So we could do this in partial pressures. We can do it in concentration. That's what we're going to do. The equilibrium constant is given in case of C. So it doesn't really matter at this point, all right? Just we're doing it in some kind of a concentration unit. And what we say is we've got 0.50 molar H2 and CO2. Those are our two reactants. We haven't started the reaction yet, so it's definitely going forward because I don't have any products over here. So that's going to wind up being 0. So let's take a look at what our change is going to be if this is our initial concentration, where our change here is going to be minus X. Our change here will be minus X. Note that the coefficients are 1 for both of these reactants. So we just have minus 1x and minus 1x. Why the minus sign? Because reactants disappear when the reaction goes in the forward direction. Over here, we're going to make some products, so our change will be plus x because those coefficients are also just 1. And so that's why we have 1x here and a 1x here. Then we simply add the initial to the change line in all 4 cases. We get 0.050 minus x, 0.050 minus x, and 0 plus x is just x, 0 plus x is just x. All right, so I've gone ahead and set up the same problem over here in just the way that you would set it up. You would make your own ICE table, ICE. I highly recommend that you put these letters up here to remind yourself what you're doing. And this is just 0.50, 0.050, 0, and 0 are changes minus x, plus x, plus x, and 0.050 minus x, 0.050 minus x, 0 plus x is just x, and x, just like we did on the previous page. Now I need the equilibrium constant expression for this reaction. It's pretty simple. All the coefficients are 1. So this is just going to be K is equal to H2 times CO2 divided by the concentration of H2O. And this is a gas phase reaction, or we would not be including water in this particular reaction because water as a liquid doesn't change in concentration, but water as a gas can change in concentration. You can have different partial pressures for water vapor. All these are gas phases, and so that's totally legit to keep including water in this particular case. Okay, so now we're going to take the information that's given. We've got a K value, we've got these values down here, and then we've got a couple of X's. And let's just go ahead and plug things in, see what we've got. We've got a K value of 0.10 is equal to X times X. That's what this is, X times X, which is just X squared. And then down here, in the denominator for reactants, excuse me, we've got 0.050 minus x times 0.05 minus x. So that's going to be 0.050 minus x, and we can square that as well. Now, this would be a fairly ugly algebra problem because we would have to do FOIL, first, outer, inner, and last on this part of the reaction. But you know what? Algebra is no fun. I'm sorry if there are any mathematicians in here that enjoy algebra. I apologize. But let's see if we can simplify the problem, make the algebra easier. Well, we see we have a squared term in the numerator and we have a squared term in the denominator. This is called a perfect square. And since it's a perfect square, I can take the square root of both sides, and that rids me of that pesky squared term in the numerator and the denominator. And so when I do that, that gives me 0.316 for the square root of 0.1, and that will equal x divided by 0.050 minus x. Now that's going to be a lot easier to solve. So we'll go ahead and multiply both sides by 0.050 minus x. It's going to cancel over here. We'll do the same thing here, 0.050 minus x. Tell you what, it's going to be easier to see if I do it over here. So this is 0.050 316 times 0.050 minus x is equal to x. So I'm going to go ahead and distribute the 0.316 through the parentheses. When I do that, I get 0.0158 minus 0.316 x. That's just multiplying 0.316 times 0.050, and 0.316 times minus x is equal to x. I'll go ahead and group my terms by adding 0.316x to both sides. So this is 0.316x. And here it goes away because I've subtracted it there. And this is going to give me 0.0158 is equal to 1.316x. The reason you have 1.316x is because this is a 1x that you're adding to 0.316x, which gives you 1.316x. I'll divide both sides by 1.316. It'll cancel here, and then divide by 1.316. That's going to give us the value for x. And that gives me, looks like 0.0120 molar. Okay, so that's my x value. And what it wanted to know was the concentration of water vapor. And since the concentration at equilibrium of water vapor is x, then that's going to be the concentration. Just as an aside, if they wanted to know what the concentration of H2 and CO2 were, all you'd have to do is subtract x from the original concentration. So let's go ahead and do that. We've got 0.050 minus 0.0120. And when I do that, 0.0380. So that's going to be 0.0380. I could go ahead and check this by taking my x value, which is 0.0120, square that, because if you remember, that's x squared. That's what's in the numerator of my equilibrium constant expression, and I can divide it by the concentration at equilibrium for H2 and CO2, which is 0.0380, which I also have to square. If I come up with something that's very, very close to 0.1, I'll know that I've got the right answer. So 0.0120 squared divided by second answer squared, and I wind up getting, it looks like 0.0998, which is approximately 0.100. I did a little bit of rounding, but in general, this is a pretty good answer for this particular problem. Okay, I know the video is going a little bit long, but let's go ahead and do one more type of problem, and then we can be done with this, all right? So this, if you look at the initial concentrations here in our ice table for our equilibrium reaction, we don't have any zero concentrations here. And without zero concentrations for any of the components, we actually don't know. We don't know which way this reaction is going. Okay, reaction goes. Does it go forward or does it go in reverse? And the reason that we don't know, if you remember, when I drew this little diagram, okay, this is where Q is equal to K. Now, since I've got non-zero concentrations for all of my components, I don't know if I'm over here where Q is greater than K and the reaction would have to go in reverse to equilibrium, or where Q is less than K, where the reaction would have to go forward to equilibrium, because you know the end result of all of these reactions is they go to the lowest energy point, and that is where Q is equal to K and the reaction is equilibrium. So I actually need to calculate the Q. So we'll go ahead to the next page where I've got a little bit easier run here. So that's going to be I, C, E. We can go ahead and fill out this part. So we've got 0.500. We've got 0.100 here and 0.100 here. Now we need to calculate Q, and we calculate Q the same way we calculate K. We've got H2 times I2, and we're going to divide that by HI squared. Okay, so let's just go ahead and let's do that calculation and compare the Q to K and see which way the reaction goes. So for H2, we've got 0.1 times 0.1. That's just going to be 0.100 squared. And for HI, we've got 0.500, also squared, this time squared because the coefficient is 2. So when we calculate that, we get 0.1 squared divided by 0.5 squared, and I get a Q that's equal to 0.04. So my Q is 0.040. And I look over here and I see, oh, K is 0.020. So Q is larger than K. This is 0.04. This is 0.02. So which way is this reaction going to run? It's going to run in reverse. Okay, so we have to run this reaction in reverse. All right, so that's going to affect the change. Since it's going in this direction, you're going to have a positive 2x for your reactants. You're going to have a negative x for both of your products because the reaction is running in reverse. And to answer your question, no, we don't flip the reaction around. If I flip the reaction around, then I'm making work for myself. I would have to take the inverse of the K. Better just to leave it in the conventional form, thinking of this is forward and this is reverse. Okay, so that's going to be 0.500 plus 2x. This will be 0.100 minus x, 0.100 minus x. And now I'm ready to put together my equilibrium constant expression and solve for x. So my equilibrium constant expression is K is equal to H2 times I2 divided by the concentration of HI squared. Okay, now I'm just going to plug in the variables. And so in this case, I've got a K value of 0.0200, and that's going to equal my numerator, which are my two products over here, 0.100 minus x times 0.100 minus x. So that's going to be 0.100 minus x squared. Okay. And I'm going to divide that by 0.500 plus 2x, and that's also squared because of the coefficient of 2. I have a perfect square. And whenever I have a perfect square, I can go ahead and take the square root. You're going to want to remember that. So when I do that, I have 0.1414 is equal to 0.100 minus x divided by 0.500 plus 2x. I'm going to go ahead and multiply both sides by 0.5 plus 2x and multiply this side by 0.5 plus 2x. Okay? And that's going to get rid of it over here. And that's going to give me 0.0707 plus 0.2828x is equal to 0.100 minus x. I think I'll go ahead and I will group my terms by adding x to both sides and subtracting 0.0707 from both sides. That will cancel, and that will cancel, and I'll wind up with, I think I'll do this over here, I'll get, I'm adding 1x to 0.2828x, so that's going to give me 1.2828x is equal to 0.1 minus 0.0707, which gives me 0.0293. So I get 0.0293. And then I just solve for x by dividing both sides by 1.2828, 1.2828. And that gives me an x value that's equal to 0.0228. 0.0228 molar. So let's go ahead and calculate the concentration at equilibrium for all the components of the reaction. So for hydrogen iodide, this guy right here, that's going to be at equilibrium 0.500 plus 2x, and x is 0.0228, and then for both, so we'll do that, and then for H2, which is equal to the concentration of I2, that's going to be equal to 0.100 minus x, which is 0.0228. All right, let's get an answer for that. So 0.5 plus 2 times 0.0228 gives me 0.546 molar. So 0.546 molar. For H2 and I2, that's 0.1 minus 0.0228, and that gives me 0.0772 for both of those. 0.0772 molar for those two guys. I can check this out by going ahead and calculating K, and it should come out pretty close to 0.02, so that would be 0.0772 squared divided by 0.546 squared. And we do that, which gives me 0.0228 0.01999, which is approximately 0.020 to a very high degree, or a low uncertainty, to very high precision. Okay? All right. Last thing, in working these problems, always look for a way to simplify the expression. Things like perfect square, where you have a square in the numerator, square in the denominator. Look for some way to simplify, and I'm going to show you another way. Otherwise, you'd be forced to use the quadratic formula, and I am not going to ask you to do the quadratic formula on a test. That's a lot of algebra, and you know how I feel about that. You will probably need to use the quadratic formula to solve homework problems, but not exam questions. Okay, that's enough.